Hello, Philip. Welcome. I am really fascinated with the book. I met someone. I went like I post on Twitter and I say like, "Do you want to go for coffee or drinks or whatever?" And I meet like a new person every day. One of the days, somebody came in with a book that was signed, and he said he's never going to read it. And I'm like, "This is exactly what I need to read right now. Like, it's exactly the topic that I am currently interested in." But could you please introduce yourself and what you do?
Yeah, well, hey, thanks for having me.
Thanks.
My name's Philip. I am a inference engineer at BaseTen. BaseTen is the inference platform. We also do training and some other sort of AI infrastructure stuff, but we've been around 7 years. I've been there 4.5 of those years, and our focus is mission critical inference for AI native companies and increasingly, scale ups, large digital native enterprise, everyone who's realizing that Opus tokens are real expensive and real slow and that they need a good alternative.
Yeah. Yeah, well, that's happening more and more now, not just like there's also like the lack of access because now we see that like there are models that are not being, I don't know, put on the market anymore. So it's very interesting to see. I think more people are going to start buying expensive hardware and like running their own inference in their own companies because it just makes more sense financially at some point. If you're spending like 150,000 a month on credits, like it makes sense for you to just like at least take a bit of that and direct it towards building up the hardware in your company. Um, so with BaseTen, like, could you tell me a little bit about the history of when you joined and what you're doing now?
Yeah. So, I think the place to start, as cool as hardware is, I love hardware. I think the place to actually start is model and thinking about the intelligence afforded by whatever model you're running. So when I started at BaseTen, I was working with traditional ML models. I was working with, classifiers built with XGBoost. Nothing like we have today. And early on, there were some interesting open models that came out, like Whisper. Whisper was huge for us because we'd been doing all of these transcription things with Wave 2 Vec, and then it didn't work. Like it just wasn't reliable enough to use in production. And then Whisper comes out, and all of a sudden we've gone from an 85% word error rate to like, or 85% accuracy rate to like a 99% accuracy rate. And what that meant was that we had flipped from, oh, this is not good enough to production to this is good enough for production. So, we think a lot about benchmark scores in this industry. And over the years, I've seen them go way up, and benchmarks that used to be nearly impossible get saturated. But in today's world, it's a lot less about does your model score, 72 or 74 on a given benchmark? And it's a lot more about, is this model sufficiently intelligent for the production task that I'm assigning to it? And that's much more of a binary outcome. It's either, yes, I can trust this model in front of my users if I've done all the work around it with the harness and the prompt and the context and everything, or I can't. And once you have a model that you can trust, whether that's an open source model you're using off the shelf or a custom trained model that you've fine-tuned on your own user traces or something, or even built from scratch yourself, then you start to think about all the serving optimization pieces. But until you have that level of intelligence sort of in your hands, all this stuff is just kind of an academic exercise.
Mm-hmm. And you said Whisper was like a huge jump, and I guess that onboarded a bunch of people into using this as a product. Have you seen the same thing with like any of the like what are the different LLMs or models in general that you've seen this big jump with?
Yeah, so I gave Whisper as like the first example almost 4 years ago at this point. There are these sort of night and day differences that happen every few months in this industry. Some other ones in different modalities was Stable Diffusion XL in image generation. All of a sudden, open source image generation is good, not unusable. There was, of course, Llama models were the first sort of even remotely viable open models. And then the DeepSeek R1 moment. There was the Kimi K2 moment. That was a big one. And obviously recently GLM 5.2. I'm sure everyone out here is running GLM 5.2. Great model. It really lives up to the hype in my experience. But what's cool is that we don't just work with large language models, which are the ones that get all the headlines. Like there have been major advances in open source embedding models. You can basically do anything with open embedding models now. About a year ago, there was Orpheus by Canopy, which was an open source voice model that led to a real revolution there in text-to-speech synthesis. So across just about every modality, there are really high-quality open models that can at least serve as a baseline for fine-tuning. And because of that, this whole industry is just kind of wide open right now.
Yeah, I definitely agree. So I started self-hosting around, well, I did the first like llama models. I found them to be just compared to what I was paying for unusable. And then again with the GPT OSS models, that was for me another like that was a sign that it's possible to get something good. Once GLM 4.5 Air came out, because that was like the first model that is even remotely possible to self-host,
Yeah.
that is actually really good, right? You people paid for it.
Mhm.
And I started buying hardware and I had to learn like the insane world that is like inference engineering. It is crazy, at least from my perspective. Maybe for somebody that's already been in it for a while, it's not so like I don't know how to explain how crazy it is because there's just so much learning. It's changing every day. It's very complicated. And there's not much products that make it easier. I would say, like LM Studios there, but the speed of Llama CPP was like it took something that maybe you could do some work with to something that you can't. And so I had to learn all of this from scratch. But
Yeah.
you wrote this book. What caused you to write this book?
Well, but before I get to there was kind of a bifurcation in this industry that I want to address, which is like the sort of self-hosted open model world and the inference as a service world that honestly I think like need to hang out a little more. So I'm glad that we are. But a lot of the work today that's done on inference is done under the assumption that you're not trying to serve tokens for yourself or yourself and a couple friends, but you're instead trying to build a AI product and serve inference to hundreds, thousands, millions of users. So a lot of the problems that local inference faces is just get this thing working. I have even at very high-end consumer, prosumer hardware, a limited amount of RAM and a limited amount of memory bandwidth on that VRAM. And so a lot of it is around the distillation of models, the quantization of models, and otherwise just kind of squishing models until they fit on whatever hardware it is. Whereas with, a lot of the work that we do in terms of building managed inference for business customers, it's a lot more about taking the sort of native expression of the model or a very lightweight quantization of it, and then pushing it as far as possible for latency, throughput, cost, etc. on 8xB200 on NVLs, like on just the best hardware in the world, which is a lot of fun for sure. But also just a different set of challenges to address. So because, as new and novel as local inference is, there's a good community there. Data center inference, I feel like, is even more insular. I've had the good fortune to be in this industry for 4.5 years. I got very lucky in terms of my choice of job in 2022. And so I realized that I had this foundational understanding of all this knowledge from working with the engineers at BaseTen for years that no one had yet taken the time to put all in one place. So I decided to do that to give people a good theoretical overview of this industry.
Yeah, and it is good. So one of my struggles is I'm not like classically educated, and I'm missing a lot of the critical information. So usually when I'm trying to read these types of books, they're very dense. They require a lot of like understanding of math and all the physics around it. But this was really easy to read. Like there's a lot of charts and graphs, and I think that makes me like more likely to get through it. So I did enjoy that. And also I felt like it ramped up, at least because I read maybe 60 pages so far. So at least until there, it ramped up pretty nicely. It built pretty nicely. Maybe you can tell us a bit about like the basics for the people, because most of my audience is actually interested in self-hosting or like making local AI for themselves better. And I think there's a lot to learn again from, you're right. Everything that was built like VLLM, SGLang was prioritized data center cards and these like really unconstrained environments, at least compared to the normal person. So yeah, I'll leave it up to you.
Yeah. So step 1, acquire an 8xB200 node. Step 2, acquire like 20 more of them so you can do horizontal scaling. Step 3, start an inference company. No, it isn't actually like that. Like the first step is actually nothing to do with inference. It's like getting familiar with what models you even need for a given task. So a lot of the stuff we do is working on, evals and benchmarks, and do you feel confident that this is the model that you actually want to run before you go and spend a whole bunch of time and energy and money like getting it to the point that you can run it. A great way to do this is just whatever APIs. Obviously, I think you should use ours. Anything on OpenRouter is good, though. You can use the first-party APIs just to test stuff out. And once you have an idea of the model you want to run, if you're doing local inference, the first step is quantization. So when you train a model, you generally train it in something called BF16, which is a 16-bit floating point number. So if you think about a model that has, say, like 1 trillion parameters in BF16, each one of those parameters is going to be a 16-bit number. That's 2 bytes. So all of a sudden you have 2 terabytes of data. And all of that data needs to get loaded into your local system memory in order to run the model. It
needs to be good memory.
Exactly. And that's just not feasible. In fact, that's not even feasible for our data center GPUs, which is why we generally run inference in something like NVFP4, which is a 4-bit floating point format. So now you're at like 500 gigabytes of memory just for weights. But you guys actually do have an advantage over on the local side, which is generally you're going to be doing your inference for like local coding, local chat, something like that, right? So that means you can generally run the model with a batch size of 1. Now, I can't have my 8x B200 serving a single customer. That's just not good business. So I have to run with a batch. And when you do batch inference, you have to assume, hang on, let me back up a second. So mixture of experts models. Tell me about your familiarity with the mixture of experts architecture.
So I've learned a lot about over the last year. I mean, all the models that I've personally used are a mixture of experts. I think I will leave it up to you to explain it, though. I think it is one of the most critical things when it comes to hardware and models.
Yeah, so mixture of experts is one of those things that's like good for the local folks and good for the data center folks. It's good for the local folks because when you think about the routing of a request through the experts in a model, you're only activating a certain fraction of the parameters, which means that you're able to run it on less hardware and it runs faster. Now, I don't get that benefit. Like I said, I can't put my 8x B200 node in front of individual users sequentially. I have to batch their inputs. And when you run at a large enough batch size, you have to more or less assume that every parameter is going to be activated at the same time. And you have to assume that you're going to need to load all of that data. So instead, we do something called expert parallelism, which is where you can put sort of multiple experts per GPU, and each GPU on the 8x node owns those entire experts. That's a throughput optimization. You probably also want to do some tensor parallelism for latency optimization on top of that. But the takeaway here is that like one of the reasons that the mixture of experts architecture is so popular is that it helps you guys out on the local side and it helps us out on the data center side. There's a lot of other things that we do on top of that are probably not going to be as valuable. We do a lot of work on the speculation side. We do a lot of, we recently rolled out some disaggregated inference, which is cool. That's when you have, so many B200 nodes sitting around that you can use multiple of them on a single serving instance and put prefill on some and decode on the others. But yeah, I guess then the last one is KV cache reuse, which probably is somewhat relevant in local serving as well. Obviously, skipping prefill is very important. It's just that KV cache also takes memory, which is the big constraint. So I would imagine that, writing KV cache to local storage or at least to RAM would be like one thing, and reading back, that's something we think about a lot on, the Grace Blackwells, for example, is can you offload KV cache from the VRAM onto the system RAM with that high bandwidth interconnect? So I would imagine, I don't know this personally, but there might be some close analog in the local inference world, which could be another, valuable optimization.
There was this post that I saw on Twitter, maybe I imagined I saw with LM Studio, which I think is the most popular desktop app for this for people to get started with local inference, and it was that most people are actually starting with their Macs and MacBooks. And one of these people is like Inferencer Labs. He's on YouTube. Reviews all the models, but he has his own like desktop app, and they do KV cache storage on SSD, and then they fetch it, and it's very smart. And I think there's a lot to learn like from how VLLM does it, like breaking things into chunks, and that could be very useful. But yeah, like I think there is very little financial incentive for people to work on single user like inference, or like like making it run on a DGX Spark or a MacBook, and I don't know where the money comes from.
Yeah,
So,
I've said before, like I love local influence as a as a developer and as just someone who's in this field. I think it's awesome that it exists, but I don't make any money when people do it.
That's true. That's true. Okay, so once you get past like selecting a model, like testing it out maybe on OpenRouter, understand like different ways of spreading them, like putting the model in like different areas. Then you come to the inference part of it, and like you are generating these tokens. For you as a business, like where else can you find? So I think there's MTP, right? Multi-token prediction, speculative decoding. Where else do you see like gains that you can maybe get if you can share this info?
Yeah, so from a business perspective, moving from the conversation of like how do I just get this up and running on my Mac to how do I build a top sort of best in class API for this, there's a bunch of different pieces to consider. And the big thing to understand is that there's sort of two classes of optimizations. And the highly technical differentiation that I make here is inside the GPU and outside the GPU. Very technical. We could call this, the infrastructure layer and the runtime layer or whatever. But it's inside the GPU and it's outside the GPU. So outside the GPU, you've got to think about your networking, your queue for holding requests. You've got to think about having users worldwide and having horizontally scaled replicas, possibly in multiple different clusters, multiple different regions, cloud providers, connecting and routing between those. You've got to think about, if a user's request comes in and then they send another request a minute later, you probably want to route that one to the same place so that you get a cache hit on your prefix. There's a lot of work that actually happens in the sort of traditional infrastructure and distributed systems world where we're just kind of like relearning all the lessons that database engineers have been dealing with for the last 4 or 5 decades. And that's really cool. And I think a often sort of overlooked piece of this puzzle, because, what happens inside the GPU is so cool. And that's where your raw tokens per second often comes from. But the infrastructure side is more about like, how do you sustain that and scale that across a lot of users? In terms of inside the GPU, do you want to like kind of walk through step by step, like how you go from I have generic VLLM and I have my model loaded into it and I'm making tokens to like I have the fastest thing on artificial analysis?
That's where I'd love to go. Yeah.
All right, let's do it. So we're going to be talking about inference optimization in the data center GPUs. And one thing that I think is really interesting about this is like, this is a valuable problem to solve. It's worth a lot of money to be good at this. And most of the things that we're going to talk about are, the punchline is this made it 20% faster, 30% faster, 50% faster, 2x faster. If you think about high performance computing, and if you think about highly optimized systems in maybe quantitative finance or other lucrative or training or like other lucrative fields where there's been more than a few years of work done, people get real excited about like 2% better, 5% better, etc. So I think that just shows how new the inference field is and how much work there is to do still in this field, which is what makes me so excited to work in this field. But anyway, let's kind of talk through it. So you've got VLLM, you've got some GPUs. Let's say you've got some Hopper GPUs, some 8X H200, and you put a model, let's say GLM 5.2, in there, and you run it. and you get, I don't know, 30 to 50 tokens per second on a reasonable batch size on a reasonable configuration. And congratulations, like you've solved inference. But let's say you want it to be faster. Let's say you want to get the fastest speeds in the world. Well, the first thing you're going to need to do is upgrade from hoppers to Blackwells, because no matter how good of a driver you are, you don't want to be driving the last generation car, right? Now, there's an issue for this. GLM is built for Hopper. If you think about, the export situation as well as just the state of hardware proliferation throughout the world, Hopper is actually a very reasonable target to write against. All your kernels are built for that, et cetera, et cetera. So you have to do the work to sort of port the model over to the Blackwell stack. This happens in the runtime layer. So maybe instead of VLLM, maybe now you're using something that is a little bit more built for Blackwell, maybe like TensorRT LLM. And then you have to go and, support like sparse DSA or whatever other new architectural quirks any given model has come out with into that framework, and into whatever your sort of custom framework is. We have a custom inference framework, but let's say you're using like TensorRT LLM or something. Then you get your Blackwell tokens. You get your Blackwell kernels. You get your support for the architecture, all that sort of stuff. So maybe now we're at like 60 tokens per second. And next, while you're already using Blackwell GPUs, so let's go to NVFP4. So this model is FP8 by default, which is an 8-bit floating point format. NVFP4, are you familiar with the format?
I am, yes.
Yeah. So in that case, but briefly, for anyone not, it's a data format by NVIDIA where you have 4 bits, and it is a floating point format. But what you have is something called dual scale factors, which preserves dynamic range. So the dynamic range is if you have both very small and very large values, these outliers often encode very important information in your language model. And so by preserving the sort of differences between these values, you're able to preserve those outlier dynamics. And NVFP4 is specifically built for Blackwell by NVIDIA, and it has a scale factor every 16 numbers, every block of 16. It also has a 32-bit scale factor at the tensor level, and that allows you to preserve quite a bit of dynamic range. And then the Blackwell GPU is like physically constructed to kind of offset some of the losses that you have by applying both of those scale factors. And now you're maybe at 80 tokens per second. Now you got to go back and test and make sure that you haven't messed up the model, that you've calibrated the quantization correctly, that you run a handful of benchmarks and the scores should be just about the same, sometimes lower, sometimes higher, just due to margin of error. So sometimes you'll run a model in like FP8 and be like, oh, this scores 75 on this benchmark. And then you do it in FP4 and it's like, oh, it scored 76. It's like, no, it didn't get smarter. It's just, margin of error between runs. All right. So now we're maybe at 80. Then there's some other stuff you can do. You can, change the nature of the traffic a little bit and, make sure that you're getting a really high cache hit rate. That's going to help out a lot. Then the next piece is going to be disaggregation. So prefill and decode are 2 very different workloads. Prefill is compute bound. Decode is memory bound. You want to use different configurations, different kernels even.
So a question here.
Yes.
Maybe you can explain this, maybe you can't, but can you explain a little bit the difference between compute bound and then memory bound?
Absolutely.
And how that affects prefill and decode?
Absolutely. So prefill, that's your time to first token. Decode is your tokens per second. To be compute bound, like prefill, means that the thing that's stopping you from getting any faster, that's stopping you from getting a faster time to first token, is how quickly the GPU can do math. If you're doing decode, you're memory bound. The thing that's stopping you is how quickly can the GPU move bytes back and forth from the memory to the compute. That's why like quantization is so valuable. Quantization helps you with both, because on the compute side, you get access to the FP4 tensor cores, which are faster. And on the memory side, you have to move less information back and forth, which doubles the effective latency or the effective throughput of your memory. And so that's why that's a valuable optimization. And it's just always important to know where your bottleneck is when you're thinking about performance optimization, because if you improve something that's not actually the bottleneck, you don't see any real like wall clock gains. But if you do aggressively attack the bottleneck, then you can see material speedups.
So when we talk about disaggregated inference, so having maybe one operation in one place and another like on different GPUs, or setting up like experts on different GPUs with GLM. So
Yeah.
I'm running on 6000s.
Mm-hmm.
And first, it doesn't fit in
Yeah.
NVFP4, so I have to prune it. I basically give it calibration data.
Mm-hmm.
I get basically the expert saliency scores, and then I decide what to preserve and chop the rest off. Then I basically pass it through benchmarking. I'll do a smaller sample because it's super expensive, usually on Blackwell. When I get the results, I expect to see losses in like, because I'm pruning for coding and agentic and English and math, philosophy, stuff that I care about. I expect to see a loss in history, a loss in other things that are unrelated. But then once I am able to get it to fit, the problem is the RTX Pro 6000s don't have NVLink. And I bought my motherboard and CPU a while ago, so I'm PCIe 4, and then I have to introduce these risers because there isn't really much cards that you could fit at home that just allow you to slot things in, especially cards that are that big. So you're losing all that speed there. And then because of the way GLM is written, I can't like host it normally. I'm not really exactly sure what they're doing because I take these off of Docker.
Mm-hmm.
Like Docker Hub has people like trying to tweak this. But in order for me to get like good context, I need to use DCP. So put the I think it's splitting the context across the GPUs, but that introduces latency, and then I get either more or less context, and it's either faster or slower. So all this stuff is like super interesting, but it's completely different problem set than I think you've been through. Maybe we
that sucks. Like that sounds hard.
It is hard. Yeah, it is. It is. But yeah, there's a lot of people working on it tirelessly. I think this is what I started seeing recently with local. Is that people are taking it more seriously.
Yeah.
Because the models are better. You have the Quen models that fit on a single GPU and work like really well. So people are excited about it. So there's all this like, Discord servers you jump into, people are like trying to optimize, doing crazy things.
Yeah.
It's very, very cool.
That's awesome. That's awesome. It sounds, it sounds hard. I'm sorry you have to do all that work just to get something up and running. I will say that the parallelism piece is interesting. We think a lot about topology as well, in terms of the interconnect from VRAM to compute, the connection speed, the NVLink between GPUs in a node, if we have maybe InfiniBand between nodes, because we did at one point look into multi-node inference a lot, and then we had to think about those kind of problems, and then Blackwell came out and more or less fixed things, so we didn't have to do that. There was a moment around DeepSeek R1/V3 when the models were getting a little bit too big for the H100s, and we had a lot of H100s back then, and we wanted to figure out if something could work. So we kind of started down that road, and then Jensen came and saved us with Blackwell. But I think that like the parallelism and how you split the model piece is interesting. The prefill decode disaggregation that I'm talking about is like a completely at the other end of the spectrum thing, where you have so much hardware that you are running into the problem of not utilizing it effectively. So that's the real issue. It flips from like, I have too much workload for my hardware to I have too much hardware for my workload. And how do I make the workload like take full advantage of the hardware? And so it's just a fundamentally different set of problems and a different way of thinking about the problem.
Can you explain it a little bit?
Yeah. So if you have, your prefill and your decode that are running on a single node, then they're kind of competing for resources, right? So the memory is being competed for, the compute is being competed for, And if we're doing batched requests, obviously we're much less memory bound than we would have been otherwise. Like we are using substantial compute to process the whole batch. And in general, just as a rule of thumb, like the more specialization you can introduce to a system, the better. Like if you have to train someone to be both fast and strong, they can get a really long way. Like NFL players are really fast and really strong. But if you train someone just for speed, you get, Usain Bolt or Eliud Kipchoge. And if you train someone just for strength, you get, the mountain from Game of Thrones. And so you can, if you're looking for truly outlier performance, you kind of have to specialize. And that's the idea behind, something like PD disaggregation is we're pushing for like truly outlier performance. We're looking at, how do we like double TPS on these nodes?
Look like having, let's say, a replica just doing decode and a replica.
Exactly. So we actually use slightly different terminology because you still might horizontally scale a PD disag system where you have multiple replicas of the entire system. So we think about it in terms of workers. You have prefill workers and decode workers. You might have, say, like 3 prefill workers to 2 decode workers. It doesn't have to be a 1-to-1 ratio. It depends on the input and output sequences, your cache hit weights, which ratio is going to be best for you. But yes, the idea is that each worker is itself an 8x node, 8x B200 node, and then a worker is either responsible for prefill or decode. Now, this does introduce a challenge, which is that the whole point of prefill is to build a KV cache, and that KV cache is sitting over here, and my decode's running over here, and how do I get these two to talk to each other? Mm-hmm. So that's where NVIDIA introduced a toolkit called Dynamo. Dynamo is basically it's a set of tools for moving KV cache information around. It's useful for cache-aware routing, for KV cache sharing and sharding and offloading. And it's also useful for disaggregation because you can use it to move the cache from the prefill node to the decode node.
So, okay, I'm going to take advantage of this situation.
Yeah.
So I have 4 RTX Pro 6000s and
yes.
I have a DGX Spark.
Yes.
Both of them are on my home network. Both of them are connected directly to the router.
Yes.
So the problem with GLM 5.2 is it requires like 500 gigabytes for a FP4 in context. That does not fit on 4 6000s.
Yes.
So I can then choose to only do the inference on these 4 6000s, forget about the Spark. Then I have to prune the model. That comes with its own problems. Now, I'm wondering if I can put the cache on the Spark, but then I would assume you need the whole model, or at least, on each part, right? You would need the whole model. That's sad.
Yeah, well, so disaggregation kind of assumes that you have just like GPUs falling out of your ears.
Yeah, that's
which is why we only really started working with it recently. It does require a complete the complete weights on both the prefill and the decode nodes. Now, you could actually set this system up if you were running, say, like Gemma or some small model that each individual one of your RTXs could serve itself. Then you actually could experiment with this kind of setup. But if you're doing local inference on a huge frontier model like GLM, it's probably not going to be the right tool for you.
Yeah. Well, so this is, the fun thing about the position I'm in is I have to think about, like, how do I do the craziest thing possible to get more to fit on there? Because it's really expensive. If you look at it as an individual, or like even, a company maybe will have, I think this is going to happen soon, where any company that's spending a significant amount of money on tokens through APIs, through like, let's say Anthropic or OpenAI, are going to start routing a percentage of that into B200s, B300s, GB300s, like a workstation per,
Really? You think so?
I think so, because it's going to be like, first you have the private information, right? Like all the private information for lawyers, psychologists, like any people in the medical industry in general. They're going to need to, because now with like the latest model, Fable, there's no way for you to opt out of data sharing.
Yes.
And I think that this is only going to get more and more difficult, because well, this is like, being on Twitter all day.
Yeah.
Maybe I'm wrong.
No,
So
I certainly agree with you on the problem. I'm heavily incentivized to disagree on the solution, but I'm interested in hearing you out here.
well, I think the solution is two-part, right? Like there's always going to be clouds that have models that are truly like spectacular that you can
Yeah.
pass workloads to. But then the average person is not passing like highly technical work to GPT-5.5 or to Opus or whatever.
Yeah.
They're passing everything, right? Like people like me, like, hey, check my email, set up my calendar, like look through my X messages. Like it's work that could be done locally. And then you have the work that needs to be done in a data center, right? Like you need the compute for it. I don't think that's ever going away. So maybe that helps ease the tension.
No, I mean, I think that a lot of people are going to buy hardware for sure. I just think, we overestimate as folks with, nice new MacBooks and RTXs at home, the level of hardware access that the average person has. Like when I look at, the computers that I was given when I was an intern at big banks, you're not running even a 500 million parameter model on one of those. And when you think about the small models where you're paying, I don't know, 10 cents a million tokens, I do agree that a lot of traffic is going to get routed away from frontier models to cheaper options. But I think a lot of that demand is going to be absorbed by APIs for small models. And that there's going to be like everything is power laws, right? I think if you look at the sort of top 1% users, that they're going to start to think about this problem, and maybe some of them are going to turn to hardware for a solution. But I struggle to imagine the sort of everyday user, setting up LM Studio and making their own tokens at home.
So maybe I would have agreed with you like a few months ago, but I'm seeing that the capability of these tiny, like the gemmas or the Quens, has gotten to the point that is like on AA, because I used probably AA is like the most trusted reference.
They're pretty good, yeah.
So I checked Qwen 3.6 35B and Sonnet 4.
Yeah.
Qwen 3.6 is like 15% better on almost all benchmarks than Sonnet 4. And it's faster.
Yep.
And you can run it on a MacBook, on like two PlayStation 5s, right? Like people are doing this stuff. But this is also true. What you're saying is that I'm kind of in a bubble.
Yeah.
So the people that I see doing this are like similar in mindset to me. Where is this going to catch on and be like a standard thing in society? I'm not sure.
Here's the way I would think about it. What is the base capability of an iPhone? What is the base capability of a MacBook Neo or a MacBook Air, the base model? You're looking at maybe like 8 gigabytes of VRAM. And I mean, Apple hardware is very, very good. Google, I think, has been doing a lot for local inference with their Gemma family. They have models in the hundreds of millions and low billion parameters. So when I think about a sort of common denominator local intelligence, I think a lot about voice, because those models are very small. I think about search, embedding, that kind of stuff. Those models are very small. And I think about, maybe some tiny instruct tune, like 1 to 4 billion parameter language models. You still, like, these things still chew battery and stuff. But if you think about, the last couple generations of hardware, iPhone 17, 16, 15 Pro, these are the kind of cutoff of where you can do local AI. And if local AI is going to be a requirement for a system, I think that the folks building it are going to want to see like majority, if not super majority, market penetration of a certain level of intelligence. But I mean, a lot of people today, like if you're still buying like a $500 laptop at Best Buy, you're not getting something that does this. So I agree that there are going to be certain baseline capabilities. And I think that within a couple of years, those capabilities are going to be quite good. But I'm a little bit more bearish on where they're at today.
I see. That makes a lot of sense to me. So you also said that, you guys used to optimize for multi-node inference, right? And you stopped doing that, or like this is less of a factor in your current work. When you were doing that, how would you optimize that? How would you think about it?
Yeah, so that was just a a really short-term experiment around the sort of DeepSeek R1 era. And it was entirely what you were talking about with interconnect speed. That's the whole game. So the first step is just like when you're provisioning GPUs, are you provisioning ones that have Ethernet connections or have InfiniBand connections? You want InfiniBand.
Mm-hmm.
And then the second piece is altering the parallelism strategy. We do a bunch of tensor parallelism. Tensor parallelism is great for latency, but it assumes really fast interconnect between every GPU on the node, like your NVLink setup. But if you don't have that, you need to either do like wide expert parallelism, where you're really shouting out the experts and letting them run independently, or you need to do what we were doing back then, which is hybrid tensor pipeline parallelism.
Mm-hmm.
Pipeline parallelism, you're going a stage at a time. It's generally bad because it creates bubbles in your pipeline. It's not great for latency, but it has very little communication overhead.
Mm-hmm.
So what you do is you do TP within each node and PP between nodes.
Yes. So I had to do that with the 3090s. It
Yeah.
started with 3090s. I got to 8, and that was like a whole thing. So I'm really interested in like these like little games or things that we could do that still haven't become standardized.
Yeah.
So an example is with CPU offloading. We were talking about mixture of experts.
Yeah.
And please let me know if
no, we're good. We're good. I was just taking a look.
All right. So with just making sure I got this right. It's lost my mind. I'll rethink of it in a second. But before then, until then, where are you most excited?
Well, like I said a little bit earlier on, I think this is something you're facing as well. Is like when we come out with a new technique, it's like this makes it 2x better, and that's very exciting. It's like tensor parallelism. Disaggregation 2x better. We just published today about a new form of speculative decoding where we're kind of continuously retraining the speculator model on live traffic. And depending on the workload profile, that's 20% better to 2x better. A lot of things, it's like, hey, this is twice as good. This is twice as good. On the one hand, that's very exciting. Like if you stack 3 twice as good optimizations together, assuming a frictionless plane, you get 8x better. And like you can see like really big performance leaps through composition of techniques today. But I'm also excited for an industry where we've made enough progress that we start getting excited about, oh, this is 10% better. And that's big news, because when you think about the number of tokens that are getting generated today and the number of tokens we think are going to be generated in a year, 2 years, 5 years, that is a massive amount of compute. That's a massive amount of power. That's a massive amount of money. And so everything that we can do in the technical optimization side to reduce that, especially, in the face of very, very overwhelming demand for tokens, I think we're going to just see massive amounts of investment in solving these problems. And we're going to get to the point where like even small optimizations are still really exciting because they're applied against large enough workloads that they materially change the amount of cost or power that's being consumed to, fulfill that demand.
That makes a lot of sense. So I did remember what I was talking about.
Let's do it.
So with so there's CPU offloading, and then going back to this REAP strategy, which allows me to figure out what to prune. One thing that I feel is underexplored is like using multiple tiers of memory and then being extremely strategic about what goes where. So with machines that have TPUs, like if you put the speculative decoder on the TPU, you get a speed boost, right? Because if it's generating faster and you can sample from that quicker. So like this is an example of something you can do. And with REAP, again, like there are usually like the end of the model. So the last layers and the first layers are really, really important. Like they have a lot of saliency. And then in the middle,
we think about that with quantization too.
Yes.
Like, maybe just quantize the intermediate layers, leave the input and output layer alone.
Yes. And going into the experts as well, like you have the same thing. Like, so that, it's heavier at the bottom and at the top, and you can basically take pieces out. And as long as the routers are retrained to deal with the situation that they're in, I think it comes. So the REAP that I have, I got the KLD down below what the NVFP4 was from the FP8. So it's pruned and it still has better KLD because I just spent like at least a few weeks just feeding it, not weeks, because I had older like GLM5 and GLM 5.1. I was able to apply the same observations onto it.
Yeah.
I already know what's good, and it performed like significantly better, and it maintained its ability. One thing that I saw was I was with somebody and they were testing the BaseTen model. I'm not saying this is any negative. I know why this happens.
No.
But
you can say negative things. I'm not going to be offended.
Doing this repetitive token thing.
Right? Oh, the S problem. Yes. Yeah, we were working on that.
So I know, well, at least I think I know why that happens.
Yeah.
When you prune, it increases it. NVFP4 increases the likelihood that that happens as well.
Yep.
So there are these like token attractors. Once it hits, the model just keeps predicting the same token over and over. Because the log, the probability of the logs is too close to each other.
Exactly.
And like you have to get temperature right and do all this stuff. So
yeah, because it only happens at certain temperatures.
Yes.
Yeah.
Yeah. So how do you take exploring these types of things that come up from optimizations? Because often you optimize somewhere and maybe you take a hit somewhere else, right?
Yeah. So obviously, like, my favorite thing is lossless optimization because then you just don't have to worry about it. But even without attributing anything to quantization or other sort of lossy optimizations, like you can introduce bugs just in the implementation of your inference engine that you have to go track down. Like you can introduce bugs in the function calling layer and in the structured output layer, like in a lot of places. So it's really just a combination of like finding the right traces, which can actually be difficult. I had a guy report the S bug earlier, and he was like, "Hey, is there a trace that you can go look at for this?" And I'm like, "Bro, I wish, but we have 0 data retention. So just like let me know if it happens again, what the prompt was."
Yeah.
And so a lot of it is okay. Well, we'll talk about it after. A lot of it is kind of tracking down these failure cases and then redoing the calibration with that information. I know NVIDIA actually just released a new NVFP4 quant that we're trying out, so hopefully that one does a little better. Yeah, there's a lot to kind of track down in that process. And one thing you mentioned, which I think is worth stating because it's restating because it's a great feature of this industry, is your work on GLM5 and 5.1 was an accelerant for working on 5.2. It was the same for us. Like we were doing performance optimizations on 5. We were doing it on 5.1. And now we did it on 5.2 and got this fantastic result. And if someone brings us or works with us to create a fine-tuned version of 5.2, like we can get the same awesome performance because it's that same architecture. So like for folks in labs who are training models, thank you for not changing your architecture every month. It actually makes it much easier for us on the inference side when we get a few generations to iterate before we have to go think of something new.
Yeah. Well, the models themselves, like I'm doing this blind, so I'm not coming at it from a principled perspective, but I could usually just stick codex with goal on something and eventually it works, right? I mean, it's probably unoptimized, code is probably trash, but it works. And I think that's like a huge challenge for at least constrained environments. Now I'm trying to get better at it works and it's really good. It's fast, it's intelligent. And so I'm bashing my head against it. There's so many things that are just perceived as a standard. Like for example, in VLM and SGLang, it expects each layer to have the same experts. Like you can't have like different sparsity in different places. And it won't run it. So you have to write you have to modify the engine. You can look at the PRs on VLM and SGL. It's like thousands of PRs, thousands of issues, people maintaining all these branches. Like it's very fractured.
It is. I mean, we have our own internal version of like everything.
What do you think is like you've probably tried SGLang and VLM. I've looked at VLM and Llama CPP. So I kind of know what is what between these two, but what are the distinctions between these two that you've noticed?
I mean, it's hard to tell a lot of times just because both do a really fantastic job. They're both maintained by great communities. The framework I personally have the most experience with is not either of those. It's TensorRT LLM, which is maintained by NVIDIA. It's also open source. We generally in sort of head-to-head see the best performance out of TensorRT LLM. The difference is, number one, it's got a very steep learning curve comparatively. They've done honestly a lot of work in the last year, especially to smooth that out and make it behave in a way that's much more VLM or SGLang like. And number two, the model support is limited. So like the thing I always like to compliment VLM on is like you can run that anywhere and you can run anything on it. Like you can run VLM on a data center, you can run it locally, you can run it on a potato. It's going to make you some tokens, and you can run it on NVIDIA, AMD, whatever, TPUs, like whatever you like. And just about any model on Hugging Face, VLM is going to be able to run it. I think that SGLang does a particularly good job in the sort of like multimodality world. They've got obviously the image and video generation runtime that's state of the art, more or less. You've got the SGLang Omni support. They do a good job of vision encoders for vision language models, which TensorRT LLM frankly struggles with. So there's a lot of benefit of SGLang in particular in the multimodal, especially like image skewed multimodal ecosystem. VLM, I feel like, also has a lot of good Omni support. I've noticed some of their Omni support more skewed towards audio. Now, you can do most things with either framework. So we end up really taking it like on a sort of model by model and use case by use case basis. And I feel fortunate that we have access to all of these really fantastic open source tools.
So I've been
like my politician answer there, because I have friends at VLM and SGLang, and I'm never going to say one's better.
I like both too.
Yeah, they're both good.
Yeah, I've been leaning more towards SGLang because I've found it easier to self-host on it. Like at least I'm getting better performance on SGLang. Things are pretty, like I think because I'm not sure if this is true, but I think it's less mature than VLM. I think there's less code.
It's somewhat newer.
It's somewhat newer. So I think maybe it's like easier to work with for people. So I usually get support on things pretty quickly. Okay, so this book is excellent. I'm very grateful. I feel like I've learned a lot. I wanted to open it up to you. I was like, is there anything that you want to bring up before we wrap up?
Can I plug something?
Yeah, of course.
So one thing a lot of people ask me is like, Philip, why would you do something dumb like take something moving as fast as Inference and put it on paper that you can't change? And, my answer is, well, all books kind of go out of date eventually. This one has a knowledge cutoff, like an LLM, so to speak, of January 20 of this year. So it's still, like, I would say 97% what I would write right now. There's just a couple of new things to talk about. And next week at AI Engineer World's Fair, I'm going to be giving a talk called What's New in Inference Engineering, which will be the first public addendum to the contents of this book. So I'm very excited about that.
I'm excited. I'll be there. I'll most likely be there.
Awesome. Sure. Well, you've gotten a preview of some of the stuff I'm going to talk about, but I'll try and go into some more depth with some slides and pretty pictures next week.
Well, Philip, I really do appreciate it. It's wonderful. And what would you recommend if someone wanted to go even deeper after this book? This is the last question.
Yeah, no, that's a good question. And actually in Appendix B, I list a bunch of books, papers, blogs, repos, resources to kind of guide your exploration in any direction. Look, this thing is 250 pages. Like, I'm not going to be able to fit everything there is to know about inference. But one thing, everything there is to know about inference is not in my head either. It's kind of scattered throughout the world of everybody working on this. So my goal here is, if you are new to the field and you want a good conceptual understanding of everything going on, check this out. It's going to give you the vocabulary to engage in this new domain. And then from there, it's going to give you guidance on where to go.
Man, that is incredible. Everything has been well thought through. You're an excellent speaker. I hope we'll see you guys in the next one.